Hi, I'm Zor. Welcome to Unizor Education. We continue talking about functionals. In particular, we will talk about how to basically determine the minimum or maximum of functionals. Well, I'll probably use the word minimum because maximum will be exactly the same thing. So, now this is part of the course called Physics Plus. It's presented on unizor.com. It's totally free website. There are no advertisements. Sign-in is not necessary, it's optional. So basically it's all free knowledge. Okay, now functionals. We do know how to determine the point of minimum, well, or maximum, for a regular function. So if you will take some function, let's say f of x, and let's say it's defined on some real segment from A to B. Now, how to determine the point of minimum or maximum, the stationary point of this function? Well, what we do usually, we do derivative. That's some function also. And we equate it to 0 and find real values x where this particular equation is true. For example, if you have function f of x is equal to, let's say, x minus 1 square, which is actually a parabola shifted to the right by 1, well, we take the derivative. Derivative of this is f df dt x is equal to 2x minus 1. That's the power and the inner function, and it's supposed to be 0. And when it's 0? It's 0 when x is equal to 1. That's exactly this point. Simple, right? And we would like, obviously, with functionals to be in some very similar position. So what does it mean? Well, it means that we have to have, let's say this is our functional. This is functional of function f, which f, lowercase f, belongs to certain class. Let's say f of x is defined on some segment AB. All right, fine. We would like actually to do exactly the same. Take the derivative. Now, what is the derivative? Well, derivative of f of x, if you remember, equal dx. What is it? Well, it's limit at point x is equal to x0, for example. We are looking for this particular point. Well, that's limit of f of x minus f of x0 divided by x minus x0, right? When x goes to x0. Or sometimes instead of x, we put x0 plus delta x, which is basically the same as delta x goes to 0. So it would be, which is the same thing, limit delta x to 0, f of x0 plus delta x minus f of x 0 divided by delta x. So delta x is basically x minus x0. It's the same thing. All right, so we really have to do this. Well, let's try to do the same with functionals. So we will do functional of something like f of x minus functional of f0 of x, where f0 of x is proposed function where functional goes to minimum, divided by f of x minus f of 0 of x, and limit when f of x goes to f0 of x. Well, that's great, except we really don't know what it is. Functional is a real number, right? From the function, we derive some kind of a number, like integral of function. Example 5, phi of f of x can be integral from a to b, f of x dx. So every function goes into a real number if we apply the functional. Great. So we kind of know what this is and this is, so we can subtract. Now, what does it mean that we subtract the function? Are we subtracting one function from another to get another function? How to divide a real number by function? Doesn't make any sense. And what does this mean? One function goes to another function. So we really have to define something like closeness of one function to another, and what does it mean when one function is going closer and closer to another function. We have to really define these and reasonably define these concepts to be able to basically do whatever we want with this. Okay, now instead of explaining how we will do it in this particular case, I will explain it on a simpler case, but it will have exactly the same problems and the same kind of solutions. So what is the simpler case where I can actually develop my technique and apply it with the functionals? Well, I did mention something like this in the previous lecture. It's called a directional derivative. But let's just explain it in a simple case of function of a point on a plane. So if you have a plane and a point P with coordinates, and we have a function of this particular point, which you can actually consider function of x, y, of two coordinates, and we would like to find where is the minimum of this function. As an example, f of p equals f of xy. What am I writing? xy is equal, let's say, x minus 1 square plus y minus 2 square. Well, this is actually a paraboloid. It's three-dimensional paraboloid, something like this. And this point is, if this is x, this is y, so this is 1 and this is 2. We are shifting paraboloid from 0, 0 by x to 1 and by y to 2. So this is a paraboloid, and the minimum is at point 1, 2. This is our point P0. That's the minimum point, which we have to find. Well, again, let's do exactly the same as we did with functionals. So we have to have f of p minus f of p0, and we know what this is because p has coordinates and p0 has coordinates. This is p0 can be x0, y0, and we have to divide by this and take the limit when p goes to p0. Well, we have exactly the same problems. What does it mean p goes to p0? Where is p, where is p0, and how do they move to each other? I mean, it's easier to define minimum as something like a minimum within certain neighborhood around the point p0. But what is neighborhood? So we have to really define what this means and what this means. Because what f of p and f of p0 we do know. It's just a number. P has coordinates x, y, so we just substitute into this formula, we get a number, real number. But what is the difference between them? So obviously we have to think about this in some creative way. Well, some people are saying that, okay, with a function of two arguments, what we do, if we will do it first along the x-axis, then along the y-axis. If you remember, we can have two partial derivatives, partial derivative per x equated to 0, partial derivative by y equated to 0, and find the function. Okay, that's possible. Find the point. This yes, this is possible. But why are we restricting ourselves to only two directions? Is it possible that function has a minimum if you will fix, let's say, x and change y? So it will be one parabola. It will be parabola if you will just cut it this way, or then you can cut the parabola this way, and you will have a paraboloid this way, and you will get a parabola in a section, and it will be minimum at this point. But maybe if you will cut it somehow at the angle, it will be different, and it will no longer be a minimum point. Who knows? And to resolve this, we are actually inventing this thing called directional derivative. So instead of just going like this, where we don't know really where what is p minus p0, we do it differently. What we do is we take any point p. This is our p0, x0, y0. So, okay, let's take any point p, x and y, and we will approach this point, proposed minimum, from here to here. Then we can take any other point p, and we will do exactly the same, and the same, and the same. And if for any direction, wherever we are going, along which line, we will have that this point is really a minimum point, then we can say that, okay, this is real minimum. Okay, so what does it mean? How do we do it? We do it the following way. We establish function point q, which has coordinates depending on some parameter t, which is equal to p0 plus t times p minus p0, which means q first of t is equal to x0 plus t x minus x0, and q, the second component, is y0 plus t y minus y0. Now, if t is equal to 0, this point is p0. If t is equal to 1, that will be p0 plus p minus p0, so it will be p. So the t is changing from 0 to 1, and it basically covers the whole segment. And if we calculate the derivative along this particular direction, and now derivative just by t, so if we will take function f of this point, and we will take a derivative by t and equate it to 0 at point t is equal to 0. When t is equal to 0, we are here. So the derivative is just a function of t, but I would like derivative at this point, so that's why I put t is equal to 0. And it's supposed to be equal to 0 for any point p. So if for any point p, derivative of this function f of q at point t is equal to 0, if this derivative is equal to 0, that means that at point p0 we have a minimum, right? So this is basically the approach we would like to take. So instead of having some kind of a God knows what when the point is going to a point, we don't know really this. We are getting when the t is equal to 0. T is approaching to 0, because that's what basically derivative at point t is equal to 0 is. So derivative is basically the tangent of the angle of tangential line, right? So if we will go with this point, we will have this parabola, and tangential line will be this, and at the end it will be horizontal. But if we will take this particular direction, it will be some kind of this parabola from the paraboloid when we will cut it, right? Then it will be different parabola, but again, at point t is equal to 0, the tangent is supposed to be equal to 0. It should be horizontal, parallel to the xy plane. So we take this derivative at t is equal to 0. Well, let's see in this particular case what happens. So this is our function, right? So function of q of t would be equal to q1 of t minus 1 square. q1 of t is what? It's x0 plus t x minus x0. That's q1 minus 1 square. Plus the same thing with y. y0 plus t y minus y0 minus 2 square. So we have to do the derivative of this by t. Derivative by t is d per dt f of q of t is equal to, this is a power of 2, so it's 2 times x0 plus t x minus x0 minus 1 times derivative of inner function, which is x minus x0 plus 2, the same thing with y, minus 2 y minus y0. Now we have to calculate it at t is equal to 0. At t is equal to 0. And this goes out. So we have 2 times x0 minus 1, x minus x0 plus 2, y0 minus 2, y minus y0, right? And it's supposed to be equal to 0 for any point P, which means any x and y. If x and y any, how can this be equal to 0 for any x and y? Only one way. When this is equal to 0, which is x0 is equal to 1, and this is equal to 0, which is y0 is equal to 2. So we have again point P0, 1, 2, as we basically supposed to get it as a minimum point. That's the only point which in any direction will give zero tangent of tangential line. Okay, so this is the way how we deal with functionals as well. So what we do is first we establish for example, function f0 of x is proposed point where our functional reaches its minimum, just for example. Okay, now what do we do? Okay, let's take any other function. Remember, from point P0 we took any point P. This coordinates will be x0, y0, and coordinates of this were x, y, which eventually we were saying that can be any value. So let's take function f of x, which eventually we will say can be any. It basically defines the direction. So from p0 to p, it's a direction. Then we took the derivative, equated to 0 at point t is equal to 0. So at point p0, basically. Okay, we'll do the same thing here. So we'll have this. And we will have a whole, like here we will have q of t. It's the family of points p0 plus t, p minus p0. So these are all points on a segment between p0 and p. And we will also do the same thing. G of x is equal to f0 of x plus t f of x minus f0 of x. Same thing, as t is equal to 0, the g will be equal to f0. At t is equal to 1, g would be equal to f. So as t is changing from 0 to 1, this function g, I can actually put g of x and t in this particular case would be kind of more correct, I would say. So this function, you can consider this as a as function which changing t would from 0 to 1 will change its value from f of x to function f0 of x to function f of x. Okay? And what we will do is we will apply our functional to this function and do exactly the same as we did with two-dimensional case. We will have this derivative by t, because functional is a real number, which means it's a real function of t. Now, f0 is proposed minimum. F eventually will be any, right? But we have to take this derivative at point t is equal to 0. And it's supposed to be, at t is equal to 0, it's supposed to be 0 for any function f of x. F of x gives you direction from f0 to f of x. Then we will move along this particular segment and we calculate the derivative along this particular direction at point t0, which means at point f0, our proposed minimum, right? And if we will find such an f0 which for any function f gives 0 at this point, then f0 would be the real minimum or maximum. So this is the way how we approach this particular thing. Now, just as an example, if you have a particular functional, let's say your functional is equal to integral f of x dx from a to b. So what do you do is we establish this function g and apply the functional. So instead of f of x, I will have integral from a to b. Now g would be f0 of x plus t f of x minus f0 of x. And that would be dx. That's my integral. I have to differentiate it by t. And have this result of this should be t is equal to 0, it's supposed to be equal to 0 for any f of x. So whatever our functional means, but in this particular case, that's what it means. And if the functional is actually the integral like this, integral is an area, right? So you basically have from a to b, if this is f0 of x, when this area, integral is an area, right? When this area would be the smallest? Well, obviously when the function is equal to 0. So if you will take this particular integral, then you will basically you will have the solution to this to minimize this integral. Well, minimize of this integral is not really a good idea. Probably you need to have something like a square, because minimum would be with negative function. It will be negative. But if you will concentrate only on the family of functions which are positive, then you don't really need this square. And in this particular case, if you will do this, you will see that basically this particular integral would be minimum when the function would be equal to 0. So this is just, it's not an example, it's basically an explanation. Now, next lecture I will probably do some example which will result in some meaningful formula for the function f0 of x, which minimizes concrete functional. So this lecture was just to explain the concept, and the most important thing which you would like actually to remember is directional derivative. That's the key to maximizing functional. And actually there is a new kind of symbol for this thing. Well, whenever you have this at point t is equal to 0, it's called variation of functional f. So instead of differentiation for functions, we define variation for functionals, and lowercase delta is the usual symbol for variation. So variation of functional is basically going to this formula with some parameter, like t in this case, and differentiation by t actually is variation of functional. That's basically kind of a definition. Alright, so again, my purpose today was just to explain approach. And approach is directional derivative. And directional derivative at point of proposed minimum must be equal to 0, regardless of the direction. And that's the point. That's the most important part of it. And I think that's probably the most important kind of concept which people have difficulty to understand. Because in case of real function of one argument, you just take the derivative and that's it. In this case, you cannot just do the derivative, but you can do a derivative in certain direction, from, let's say, f0 to f, where f is something, some other function, where functional is also defined. So you take this derivative and then say, okay, we have this derivative along this particular direction at point f0. Fine. Let's change to another f and another. And so for all of different functions f, this directional derivative at point f0, when t is equal to 0, must be equal to 0. Then you got it. Okay. That's it for today. I do suggest you to read the notes for this lecture. So you go to Unizor, go to Physics Plus, and the part of the course Physics Plus is called Variations, and in the variation I have this particular lecture. It's minimum and maximum and variation. It follows actually to other lectures. What is basically minimum and maximum of functional? Different definition, but different definition do not really allow the calculations. This particular definition, using derivative, directional derivative, gives you the tool how to calculate it. That's it for today. Thank you very much and good luck.